Hello, Engineering Physics 2 class. Sorry I couldn't be there, but I had some things I wanted to share with you. So this is a picture from the Hubble Space Telescope. It's of a spiral galaxy called M74. Now, the reason that they give it names like that is because there are so many galaxies out there. Our universe, it has tens of billions of galaxies out there that we've seen, and there's probably more that we don't even know about. And as we've been talking about, it turns out that probably most stars in the galaxy have planets. So as you can see here, when you look at this galaxy, it's full of trillions of stars, or billions of stars probably, and each one of those stars probably has a planet around it. It's very likely, because we have been discovering that as we search the night sky and we look out at the stars, most stars that we can see have planets. It appears to be very common. We don't know if there is life on any of those planets. That's something that is hotly discussed right now. And that brings us to our topic for today. We touched on it last time, which is center of mass. And it turns out that using the center of mass, we can detect planets around other stars. It's not easy, but you can do it. And we saw that last time, Jupiter is so massive that it actually causes the sun to, in a way, orbit the center of mass of our galaxy. So just as Jupiter is orbiting the sun is also orbiting Jupiter. They are sort of dancing together. It would be like if I held my arms out and I held my sun and I started rotating. So he's much lighter than me, he only weighs about 65 pounds. If I held my arms out and I spun him around, I would have to lean back too. And so my center of mass would be displaced. So that system would be somewhere in between us. And we found that the center of mass of our solar system is somewhere between Jupiter and the sun, probably right outside of the surface of the sun. So that means every year our sun does a complete rotation. And if we were an alien species looking at our solar system from somewhere else in the galaxy, we could detect a planet here using the center of mass. Life on other planets is something that people have been searching for a long time. Something that's captured the imagination of people since probably the 1800s, when H.G. Wells first wrote War of the Worlds. If you've seen the latest version of War of the Worlds, it's quite entertaining. I saw the first episode. They mentioned that there was a signal emanating from an exoplanet in the habitable zone. Now, that's a very interesting concept, because that is the ultimate goal of finding exoplanets, and especially ones in the habitable zone that are roughly the same size and mass as the Earth. Because if we did that, then that would probably be the most likely candidate to find life. Now, to understand how we do that, we need to understand about the center of mass. And we did that. We found Jupiter, and I sent you an article, and well, it was an article, it was actually a web page, and let's take a look. Ah, yes. So, um, so it says here, imagine that we measure the spectrum of a star and we see it moving towards us. And then a couple years later, we look at this spectrum and we see that it's redshifted. And then we see that it's blue shifted again. Now, as stars emit light, we know what frequency the light is supposed to be from that star. Astronomers have identified a whole host of stars out there, and they know very well what the frequency of the light emitted from those should be. And that's because of the elements that are in each star, specifically our sun. We know that it's hydrogen, helium, and it's got a few trace amounts of heavier elements. And as we look out into space, we know what the composition of these stars are. What's interesting is that everything on our planet is from a star that exploded. All of the mass that we have was created in the explosion of one, two, three, or even more stars that reached the end of their life cycle and exploded. That's, for example, how we have very dense elements like metals, iron, the rare earth elements. These were created in several generations of stars after the Big Bang. That's the only way that you can get heavier elements. But so we know what the chemical composition of stars should be, and we know what light they emit due to nuclear fusion. And nuclear fusion is a process where we convert hydrogen into helium, and it really gives off a great deal of energy. So we know what the frequency of the light is, and we can detect subtle changes in that frequency. Now, as we looked out into the universe, so we see here, this is a cartoon up at the top of, say, a star orbiting a planet. So this could be our sun, and that could be a planet like Jupiter. Now, Jupiter really is the main contribution, and if I draw a picture here, then center of mass will probably be, oh no, not there. Oh, jeez. Put my pen. Oh, I can't do it. Can't find the center of mass. Oh, there we go. About maybe right there. Up a little bit. There we go. There's a center of mass. Not so easy. Let's make that a little bigger. Oh, jeez. You know what? Forget that. Okay. Let's get rid of these marks. All right. Let's make our mouse. Let's click on our mouse. We're going to blow up the web page. There we go. Okay. If I go back to my annotation, I'm going to draw, and the center of mass would be roughly somewhere in there where the distance shouldn't change. There we go. So inside of the sun, right about there, there's the center of mass. Oh, it's close enough. You know what I'm talking about. So now if we looked at our sun at a great distance, we would not actually be able to see the wobble. We couldn't see it moving back and forth because the distance really is just too great. We couldn't see the sideways motion. We could see slight changes in the frequency of the light. And what that means is that the frequency of our light coming from these stars, if a star is moving towards us, the light becomes more blue. The wavelengths get shorter, the frequency gets higher, and it looks blue. If something's moving away from us, the light becomes red shifted. It becomes more red. And so we can detect these changes in frequencies, and we can see that, yes, indeed, this change moving towards us and away from us is cyclical. And it's said in this page that this could happen over the course of several years. So uh, if you were looking at a particular star out there, you might have to observe it for 2, 3, or even 5 years. It would be nice if you could see 2 complete orbits of those heavy planets around the sun, so that you could really say for sure that yes, this is cyclic, and we know what the period of a year is in this system. Now, I wanted to look at what the shift would be due to other planets. And so I have on the webpage here, I have a list of the mass of all of the planets in our solar system. And we see that mass of Jupiter, let's look at Jupiter here. There's Saturn, Jupiter. So Jupiter is 10 to the 27 kilograms. That is completely massive. And the closest one to that is Saturn. Saturn is 5.6 times 10 to the 26 kilograms. Okay, so that means that really the center of mass is mostly going to depend on Jupiter and the Sun. If we go over here to Mercury, Mercury is 10 to the 23 kilograms. It doesn't even, the Sun barely moves. Mars, 6.3 times 10 to the 23. Earth is a little bit bigger, 6 times 10 to the 24 kilograms. We really don't have a big effect. Now, Neptune is actually up there with Saturn. So Neptune is also 10 to the 26 kilograms. But really, it's Jupiter and the Sun. That determines the center of mass of our solar system. So let's go back to okay, and of course the asteroid belt. It only has a mass. I think it was 10 to the 23. Let's go back here one bit. Oh, the mass of the asteroid belt, it was small. It was much less than Jupiter. It was about 10 to the 23, and the mass of the Sun is 10 to the 30 kilograms. So it really, I have a cool picture of our current. I lost it. The current position of our planets. Current position of planets in our solar system. Live view of the solar system. Okay, so here is our planet, or our solar system, and sun's moving around there. Okay, so really, Jupiter and the Sun are the only things that really matter for this. And if we look right here, that would put us, if we draw a line from the center of the Sun over here to Jupiter. No, that's where's Jupiter? Oh, did I screw that? Jupiter, where are you? Well, I guess Jupiter and Saturn are pretty close in alignment. I guess they are right about there. Well, if Jupiter is about right there, and then it's not really that close to Saturn on this map here, it is, but that's fine. Now, okay, so that would mean that the center of mass of the solar system is about there. There's our center of mass. Now, Pluto is out here. Of course, it was demoted to a dwarf planet. There's Aries, Makemake, and Haumea. And then, of course, in the asteroid belt, there is a Ceres right here, which was also upgraded to a dwarf planet. Now, when they first discovered Ceres, it was considered a planet, and that was actually demoted. So, even though we've lost Pluto, and we're all sad about that, we did gain a new friend, and these are dwarf planets. Remember, they're not actually planets, even though when I grew up, Pluto was a planet. Am I salty about it? Absolutely. Whatever. Okay, so let's get back to our lecture here. You never know what Zoom is actually putting on the screen. Okay, so we get back here. We saw before that the center of mass of these particles moves like a point particle. So if we threw it up in the air, the center of mass here would move just like any other projectile. This is true for baseball bats, it's true for solar systems, and it's true for galaxies too. You could treat the center of mass of the solar system, approximate it as a point particle. You could do that. And if we go up here to our live view, M74 is a spiral galaxy. So this would be something what the Milky Way might actually look like at its center. Of course, you can actually take a picture from above the Milky Way. Why not? If you were here, I would ask. And I would pause to give you time to think about that. Why couldn't we take a picture from up above down in the Milky Way? Well, the answer is it would take so long for the satellite to get up there that we'd all be dead, long dead. And because we are in the Milky Way, we're actually in the disk. So when we look out in the night sky, the Milky Way looks flat. And I hope the next semester we get the telescope out. You guys will come back to SLU. We'll be taking, I hope to see all of you in engineering physics too. We'll get the telescope out and we'll try and we'll look at the Milky Way. We'll look at the moon and we'll see what we can see. We use this formula to find the center of mass of our solar system, and we mostly just care about Jupiter, and d is the distance from the sun to Jupiter. This would tell us how far the center of mass is away from the sun. Now we could do this for arbitrary distances. If we didn't set the origin to be the center of the sun, then we could use this formula. And x1 would be the distance from the center of mass to the mass of particle m1. And then this would be, x2 would be the distance to particle 2. So if we say here is our Sun-Jupiter system, okay, and we put the origin at the center of mass, and then x1 would be right here. This would be, and this would be the mass of the sun, and so there's x1, that distance. Then x2 would go all the way out here to Jupiter, so this would be x2, and then m2 would be the mass of Jupiter, the Jupitonian mass. Yes, that's what people would be called if they lived on Jupiter, Jupitonians. Now, didn't know that, did you? the center of mass is in the same location regardless of the coordinate system used. So whether or not you set your coordinate system to have the origin of the center of mass, center of sun, it doesn't matter. You can move back and forth between these two systems. The position is not affected by your coordinate system as it should be. Now we could do this for any number of particles. So here we could fill this in for the mass of all the planets. We know that the sun here, we said that was 10 to the 31 kilograms, and Jupiter was a whopping 10 to the 27. Oh, that was supposed to be 10 to the 27 kilograms, right? And Saturn and Uranus are 10 to the 26, right? And so we got another 10 to the 26 over here. So we can probably throw the rest of those away. Strictly speaking, do that. You could start adding Pluto in over here and Makemake. At some point, you might ask yourself, why? What's the point? Pluto's so small. It is a planet, even though it's smaller than the moon. That's true. No, strictly speaking, you'd have to do this in X, Y, and Z. So to find the X position of center of the mass for our galaxy, we could get rid of Z because we could just say, well, Z is right in the middle. We know where the center of mass is in the Z direction. So if we were looking at our galaxy from the side, right, we know that Z is right here in the middle, not too far spread out. Now, if we look from the other sides, okay, here's our, say this is the Milky Way. I'm gonna draw a big old Milky Way here. Oh, there's the Milky Way. Pen is kind of laggy, but whatever. It's fine. Okay, then we would have, say, X over here, and we'll put Earth on the X-axis. That seems like a good thing to do. And then this would be Y. So, but we do have a symmetry in a galaxy. It's roughly disc shaped. Most galaxies are symmetric. Ours is no different. So we can easily find the center of mass of our galaxy. Okay. Now, strictly speaking, we can do this for vectors. Okay? And this big M here is the sum of all the masses. So however many masses you have in your system, okay, just add them all up. That's going to be the total sum of all the masses. I equals 1. And this is M1 plus M2 plus dot 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 plus M. Okay. That's our total mass of the system. We could assign coordinates to these, right? So we could, for each of the planets, assign an X and Y coordinate. We could say, well, the Earth is, or Jupiter is along the X-axis. That would really make our life easier because we know that the rest of the planets don't matter. So if we set Jupiter for our solar system, so here's our sun, here's Jupiter. Okay, we know the Z direction doesn't matter. We could put Jupiter right along the X-axis here. Okay, there's Jupiter. It's along the X-axis. Then we really don't have to care about Y. So we can get rid of this guy, get rid of this Y, and we only need to deal with this in one dimension. We'll just say, those puny planets, they don't matter. Let's get rid of them. Useless. Of course, this is in vectors, and so strictly speaking, we could write the center of mass as a vector, and then we could write a vector to each of our planets. Okay? And then this vector here would be the vector to the center of mass. Okay, so let's draw let's draw a picture. Okay. So here is our there's the sun. Okay, let's try and get Jupiter over here. Okay. We could really put our coordinate system anywhere we wanted to. And if we put it, say, over here, and then we would have a vector over here. We'll call this RJ. This will be position of Jupiter. Then the sun would be right up here. This would be r hat times s. And then our center of mass would be right out there. Okay, so we could think of this in terms of vectors if we wanted to, and it would be much better if we could reduce it to a one-dimensional system. Now, down below here, if we had an odd-shaped object, we can integrate that using the mass and find our center of mass that way. So we could, now, this is the discrete case up here for if we have point particles, but down below, that would be if we had, say, a solid object like this marker. So then we could integrate our mass and see how the mass is distributed along the x-axis. And I am going to bring this video to a close for now. We will continue more next time. So please look for another video. And thanks for watching. And I hope to see all of you on Friday. Thanks.